So the first section of this unit was about equations, and this one now is going to be about inequalities. So we're going to just do everything graphically here with the inequalities. That means we're going to add in two things to our graphs. Stuff we've been doing forever is the line or a curve going to be solid or dashed, depends if it's equal to or not equal to, and where does it shade. The other goal that we're going to deal with that we'll see appear in the homework is that we will give you the picture, the inequalities graph, and you got to work your way backwards and write the systems of inequalities. So once again, if it's solid or dashed, this is one of the big things we're going to have to take a look at. It depends on if it's equal to or not equal to. So dashed if it doesn't have the equal to. If you draw a line underneath, it's got to be a solid line. Okay, and the other way is to decide where you shade. Okay, when you shade, you're just going to use test points. And if you have a system, it has to make every single one of them true. One of the things we have to be aware of that you didn't have to with the lines is your domain issues. So when we get to logarithms, there's a vertical asymptote, and the domain is only greater than that x value. So when you're shading above or below, you do have to stop whenever you hit that vertical asymptote. So you've got to be aware of that. All right, so we're going to see several examples through here. I'll start with just one at a time, kind of remind you and review some graphing issues we had earlier this year, like with the square root, that negative, that horizontal flip with a horizontal slide. We're going to talk about how to deal with that. And then we will start moving into special things with logarithms, and eventually we'll get to systems. So in this particular problem, first thing I'm going to note is that this is going to be a dashed curve because it's not equal to. The second thing I'm going to do is I'm going to go ahead and rewrite the inside of the square root. I'm going to rewrite that radicand as -1 times a quantity x minus 3. So I see two horizontal changes. There's a horizontal flip. You can say flips over the y-axis, reflects over the y-axis. And it's going to go right 3. And we'll see it also goes up 2. Now, some people will say it goes left 3 and then flips over the axis. When you do that, the whole thing's, you got to move it left first and then flip it with that big space. It's a little bit harder to deal with that. But technically speaking, when you finish this problem, it is going to go right 3 from the original graph. Okay. So we know we normally have the point 0, 0, 1, 1, 4, 2, because it's a square root graph. So you start at your locator point at 0, 0, you go right 1, you go up to square root of 1, then right 2, and up here. So when we take a look at this and we want to do our transformations, break those two apart. I'm just go move one at a time, okay? So I'm going to take this first one. You cannot horizontally flip it. It's on the axis. Then we're going to go right 1, 2, 3, and then we're going to move up 1, 2. Then I'm going to take this point, flip it, move right 1, 2, 3, up 1, 2. Take this point over here, flip it across the axis, right 1, 2, 3, up 1, 2. And then I'm going to go and draw. Now, if you wanted to, you could find your locator point and say, hey, I'm going to move left since the horizontal flip and go out a perfect square. So you go out 1 and then go up to square root 1. Then you can go out 4 and up 2. Or you go out 1, 2, 3, 4, 5, 6, 7, 8, 9 and go up 1, 2, 3. So however you learned how to do this or what made sense to you, you can stay with that. Now, rather than draw a solid curve here, I'm going to do my best as I can to draw the curve, but with a dashed curve. Okay. So that's one of the two things we have to add in our graphing with the inequality. The other thing is where to shade. So I'm going to pick a test point. The best way to go for your test point is go to your locator point and move up, down, left, or right, whatever makes sense. Now, I can't go right on here. One of the things we have to note about this, the domain of this, x, has to be less than 3. Because if you put something like 4 in for x, you'd have negative 4 plus 3. And if you square root negative 1, you get imaginary numbers. So I know there's nothing that can be on the right side of that little vertical line. It is not an asymptote. It's just something to help me out. So it can actually land on that line except for at the curve. So I'm going to go pick this point right here, a nice easy one to calculate, something underneath my locator point, like 3, 0, and I'll test that point. So when I go plug that in there, I put 0 in for the y, put 3 in for the x. When we pick a locator point, it kills that parent graph off. It makes it become or that parent function becomes a 0. So I'm getting 0 is less than 2, which is definitely true, which means at this point right here at 3, 0, it is the solution. So everything below here works. Okay, all these numbers right here work. Okay, these numbers are not going to be important. And then everything over here works. So some of us know that if the y is less than, then you're going to shade below the curve. Just be careful when you get to non-functions how to deal with that. So there's my graph of my inequality. Again, your domain does make a difference. So you don't shade anywhere down over on the right side. Let's try another one. Okay, I have a dash curve again, so equal to. I see that my n right here, I know it has to be greater than 0, so I know that x has to be greater than 1. That means I have a vertical asymptote at x equals 1. So let me go ahead and do this. This is from our last unit. Okay. And then I'm going to use my parent function to help me out. So I'm just going to do transformations. This is going to move right 1, up 2. Now, one of the things that we saw when we were grading your test, some of us did not have some of those very key points clearly marked. We were just too concerned about just using a table and using, the calculator to calculate some points for us. But we really need to know the key points because when we get to systems, they're most likely going to be the points of intersection. So in a logarithmic graph, we normally have a point right here at 1, 0. 0 is our exponent, which would make the base to the 0 become 1. So you get the point 1, 0. It's going to go right 1, up 2. And we look over the graph. Normally you have whatever the base is. In this case, it's 4 and 1. So normally on that log base 4, we'd have a point 4, 1. We're going to go right 1, up 2. Normally we'd have a point at 1/4, negative 1. When the exponent's negative 1, the base 4 becomes 1/4. Go right 1, up 2. Use a dash curve. Now there's a little itty bitty tiny space between our logarithm and that vertical asymptote down here in this tail. Okay, so now we got to go do a test value here. So the key point, the locator point, was where 1, 0 gets transformed to. So what I'm going to do for that one is I'm going to pick something above or below it. I like to get 0 as one of my coordinates if possible. So I'm going to test the point 2, 0. So let me put 0 in for the y. This becomes log base 4 of 2 minus 1, which is 1. And we should know that any log of any base of log base 4 of 1, if there's a 1 here, that's 0. So we got 0 is bigger than 2. That is a false statement. 0 is not bigger than 2, which means this point right here cannot be a solution. So let me erase it. It's not a solution. So that means the other side is going to be a solution. For those of you who learn that y is greater than, we're going to shade above, then you can use that. But don't forget you got this little tiny tail all the way through here. There should be some shading going on in there. Okay? But on the left side of that shading, it can't actually, x can never ever be 1. So there's a little dashed line right here. All right, let's do another logarithmic graph. And let's take the issue we had with that square root. So let's put it all together. We got that horizontal flip and a horizontal slide. So I'm going to just take the negative and x minus 2, factor out. So now it becomes x plus 2. So this tells me the graph is really going to move left 2, up 5, with a horizontal reflection. Or if you'd rather say reflects over the y-axis. You can do that. I know that my domain is going to be x is less than, because we got that negative, it's going to flip our inequality, and what makes this 0 is -2. So our vertical asymptote is going to be x equals -2. So I'm going to go ahead and graph that. And then I'm going to do my take my parent function and just flip it. Our ordered pairs that are normally on the parent function, we would have 1, 0, 3, 1, 1/3, -1. Remember, the y coordinate's the exponent, and then when you take your base, which is 3, and raise it to that exponent, these are how you get the x coordinates. So let me take the point that's normally here at 1, 0. I'm going to horizontally flip it. Then I'm going to go left 2, and then I'm going to go up 5. Okay. Now, I can do that with the other ordered pairs. I can take the 5, 1, and flip it, and then go left 2, and then up 5. Another way to think of it, the distance between the vertical asymptote and our point when the exponent is 0 is 1. So when the exponent is 1, if I'd move 1 up from that, the distance of your base is, sorry, it's 3, not 5. It would be 3. So 1, 2, 3. Let me show that flipping again. All right, so it would be 3, 1, flip, left 2, up 5. Then we'd have 1/3, -1, flip, left 2, up 1, 2, 3, 4, 5. So if this is when the exponent's 0, here's when the exponent's -1, should only be 1/3 away. So if I go when the exponent is 2, so here's our locator point, the exponent's 2, exponent's the y coordinate, and then the base is 3, so 3 squared is 9. I can move over 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. You'd have a point there. Okay, something else I should make a note right now, because I'm going to need it. This graph is solid because it has the equal to here. Okay, so we're going to draw our graph as best as we can by hand. This again, where your graphing calculators or Desmos fall apart on you, they can't graph this going down forever. They have a really hard time with it. They don't have enough pixels. We do expect the graph to have a range of all real numbers for that curve. All right, last thing, test point. So my test point right here, underneath our locator point, where the point 1, 0 got transformed to. So I have what? -3, 0. That's what I'm going to test. And when I plug that in there, I get what? 0 is less than or equal to. When I put in the -3, that's going to become what? 3 minus 2, or log base 3 of 1, which we know is 0. And we have this plus 5. So yes, 0 is less than 5. That is a true statement. That means that test point that we use should be on the shaded region, in the shaded region. So we're going to shade this region right here. And again, some of you are going to look at the inequality and go, oh, y is less than. There we go. We can do that. I'm going to warn you, if it doesn't have y by itself and you use that method, you better be very, very careful, because if you have to get y by itself, divide by a negative, that's going to flip your inequality and it's going to go the other way. Using a test point is probably the safest way to figure this out. All right, so we've taken care of some old graphing issues with a little bit of inequalities. Now let's start talking about systems. So let's come back to a conic section, parabola with y squared and being a positive. So this one's going to open right. So this is the type of graph we have. It has a vertex of 0, 0. 4p equals 4, so p equals 1. That means the 2p is 2. That's going to help us get our focus. It's what the p is going to help us get, and then the 2p gets us last 2 points. This graph is going to be solid. So let me plot the vertex, 0, 0, opening to the right. P is 1, so there's my focus. And then I'm going to go the other direction, 2, up and down. Use a solid curve and try to draw my graph as best as I can by hand. The reason why I marked the focus. Your focus was at 1, 0. The focus of any conic section is an excellent test point for graphing, the focus or the center. But for a parabola, it doesn't have a center, so the focus is the absolute best. So we're going to go plug in 1 for x, 0 for y. We have 4 is less than 0, which is false, which means the focus is not in the shaded region. Now, I'm not going to go shading all the way this time, because when no word is written on a system like this, this means and, or intersection. So I have to take a look at what the final answer is going to look like. So it's going to be something that involves this, but maybe not all the area that I shaded. So now I have to go to the second inequality. If I see it's going to be solid. And if I pretend that inequality was an equal sign, then I just have x equals 1, which is a vertical line. Okay. So I have this line right here at x equals 1. And this one says x is greater than 1. Well, 2 is greater than 1. I don't need to do a test point on this, but if you need to, go ahead. We're going to shade to the right. All right. So when I look at this, these were both solid. We're going to have these curves here. And then this is the area that's where they're both shading. So red and purple together, or red and blue together make purple. So that's what I'm going to do with my graphing. So if it's just got blue shading or just got red shading, it's not part of the answer. It has to have red and blue. Now there's something we're going to ask for. It's these things called the vertices. The vertices are the points that we would have looked in our previous section for solutions to the equations, but they have to be corners of the shaded region. Sometimes you'll get solutions from our previous sections that are not solutions to the shaded regions. We only want these points. These are the points that you would have used in Algebra 2 when you did this thing called linear programming. We will get to that at the very end of this course. We'll come back to the system of linear inequalities, or systems of inequalities, and we will do some linear programming then. Okay, make sure you state the vertices. All right, got a couple more problems. This one says graph the system of inequalities and state the vertices. So I'm going to graph one of them in blue, one of them in red, and then I'll get the overlapping part in purple. So when I look at this graph right here, this makes me think of our polynomials. It's factored. And the zeros of this polynomial are 0, 0, 1, 0, negative 1, 0. And if I multiply it all out, it'd be an x cubed. So the end behavior, left side goes down, right side goes up, no multiplicity. This is going to be solid. So let me go plot those points. The only thing I don't have right here is the absolute, or the max and mins. So if I want to go to Desmos or I want to go to use the graphing calculator, I can go find those. For the purpose of this system right here, I don't think we're going to be so picky about the extrema points unless we specifically say graphed have the right extrema points. So I'm just going to turn around at some point in time. They're probably not the right turning points. but we're more concerned about understanding what the graph's going to look like in this problem. The last thing I have to do is shade. Notice 0, 0 is a very, very bad test point because my graph goes through 0, 0. So how about I pick something like 0, 1 as a test point? I'm going to test 0, 1. And when I put 0 on the right side, it gets 0 times a bunch of stuff, which is 0. And that is a true statement. So I'm going to shade above the curve in this problem. And then I graph the other inequality, which is very quick and easy. It's a horizontal line. In fact, y is less than or equal to 0 means below the x-axis. It is also going to be solid. So there's my y equals 0 and shade below. And finally, let's go get the areas that are shaded in blue and red. So we have a vertex at 1, 0, a vertex at 0, 0. There is a vertex here at negative 1, 0, and we have this bottom left region that's shaded. Let me state my vertices. And we're done. All right, so this time there's 3 inequalities graph. Okay, not a big deal. Let's just continue with it. So we have this graph right here. Y is less than or equal to x cubed. So we know what that shape looks like. It's a parent function, no transformations, solid. And then 2, 8, so it'd be way up there. So and then we just have to graph the inequality part with shading. Okay. So for a good test point, how about I use 0, 1, which would give me a y value of 1 and x value of 0. That is a false statement. So we're going to shade the other side of the curve. My next one, a lot of people for some reason struggle with this. This is 1x plus 0, y equals mx plus b. We had numbers there, it actually sometimes is easy. Okay, so our slope is 1, our y-intercept is 0, 0. This is solid. So use your slope, graph it accurately. If we do a test point, how about we test something right above our y-intercept? We get 1 is bigger than 0, that is true. And then the last one that we have right here is x is less than 0. X equals 0 is the y-axis. And less than that would be on the left side. So here's x equals 0. This is going to be dashed. We're going to shade on the left side. So my final region that I'm going to shade has to be purple, or it's going to have to be the red, the blue, and the green. So that would be this little tiny piece right in here. With a vertex at 0, 0, another vertex at negative 1, negative 1. Now, negative 1 satisfies the systems. 0, 0 technically would be an open dot. So We're not going to get that picky on that one, but technically it is open. So let me get a little fill color in there. Okay. All right. Normally we wouldn't do this on the test too often, but we might throw one on the quiz, maybe a really simple one on the test. But most of the time there'll be solid ones on these problems we ask for vertices. Let's take a look at a curve we haven't seen since the last unit. We haven't seen the last few examples. An exponential curve. It's just a parent function. This one's going to be solid. Got a horizontal asymptote at y0. Parent function at the exponent 0, we would get 1. So 0 x is your exponent. If we get exponent 1, we get our 1 3, negative 1, a third, 9, and so on. Since y is by itself, I could do this without a test point since y is greater than, so we would change y. But if you need to do a test point, you could test something like 0, 2, 2 in for y, and 0 in for x, and you get a true statement. The other one's very simple. It's a line with a 2 and a y intersect. So 1. It is also solid. A good test point would be something that's not on the y or above or below the y intersect. That's 0 in the column. I think it's 0 bigger than 1. So let me go to my y-intercept right here. We go to my slope, which is 2. I'll draw the line, solid line. All right. Kind of not the most perfect line right there. And then we are going to shade that line away from 0, 0. So this side. So when I graph the intersection, it will be the exponential. We'll hit that point. We'll go straight in a line. Hit this point here, and then follow the exponential. And then this will be our region. We have a vertex at 1, 2, and 1 at 0, 1. All right, our last problem. In our last problem, we are asked to write the inequality of this graph. So we're getting what in the tool speaking of the inside circle is going to be solid, the outside circle is going to be flat. These are conic sections. Write the equation of the conic section. So the circle, we need to know the center. So for the inside circle, our center is what? -1, -2. And our radius is 1. And it's shading when something's bigger than that radius. Okay? We'll use the center as the inequality. So we have x minus the x squared plus y minus y squared equals our radius squared. We know there's going to be equal to. We just need to figure out the inequality we need. If I put in my center and make the left side 0 at 4, I want to make that false. Center is not a solution to that inside circle. It's sitting outside of it. So I want it to be a false statement. Make that a false statement and inequality go this way. Another way you could think of it is that when we plug in our x and y, we want it to be bigger. It should be bigger than the radius. There's one of our inequalities. This is an and inequality. I don't need to write a word, but if you feel the need to, not the word or, can use the word and. The second inequality would be this dash circle right here. So we're going to take a look at that inequality. Okay. Go a different color, a little bit better. This is the one we're talking about. So it does not have the equal. It has the same. It has a bigger radius. Radius is 1, 2, 3. There's our radius. So it's going to look very similar. We call these circles. I'm going to use a 9. But this time I want the center to make true. So let's center and I get 0 to the left, 9 to the right. I want the 2 and 2 given to get the center is a solution to that outer circle. I'm going to have less than 9. No equal to because it's dashed or dotted, whatever you want to call it or whatever you call it. So these are the two inequalities that we have to use in putting the pencil to get this. All right, your homework for tonight for day 1 of the inequalities is and all you have is 10 problems. So I'm going to give you a warning on one of the problems. You'll see something that looks like this. What that really means is 0 is less than x, and x is less than or equal to 1. So C1, maybe instead of a 1, you might see a y here. Okay. When you get to this one right here, you might want to flip it around. This means the alligator must turn around. Y is 1. You just might want to think about, oh, that's a line, and put in your slope and y intercept. Don't let this mess you up. If you're using the word or, you have to change what's shaded by the first or the second. You won't go just the overlapping. Anything that's shaded is shaded. Make sure you know the difference between or, which is a union, and, which is an intersection. All right. So make sure you do your 10 problems, and we will probably have to do for day 2. There will definitely be a quiz on day 2.